Okay, we're allowed to solve this first problem in any way we want. So we know a little bit of information about them. You could do guess and check. It takes a little bit more because there's three of them. Um, but I would recommend putting someone's age as X. So if we put Jane's age as X, then we immediately know that Skylar's age one more than twice of Jane's age. So twice of eggs, age would be 2x, and then plus 1, that's the one more. And then we know that Skylar's age is half of Jack's age. In other words, Jack's age is 2 times Skylar's age, so we can just multiply that by 2 to get his age. Once we get all of them, we add them up. We know that their total ages is 45. We solve for x to get 6 for x, and then we can get each of their ages. Second one, so we know we're using the numbers 1 through 9. If we add those numbers up, we get a total of 45. That's going to be the total amount in all of these boxes, meaning that each row, since it all has the same amount, will have to have 15. If there's 45 total and 3 rows, each column will have 15. Once you get that, maybe start on this row, get the 6. Now you know the 8 and 6, get the 1. At this point, you could get the diagonal down here and then fill in the others. Okay, problem number 3. We have to analyze the different clues that were given here. For example, we're looking for the word for father, so we see that it's in the first and third statement and not the second. We see that the word maca is in both of those. Notice there's no other words that are in both the first and the third there. You might notice that Barubi's there, so could that be father? Well, one of the things that we could also know, clues to help us know that that's not father, is that Barubi appears in the second sentence and the word father does not. So that would rule out Barubi if we had to make a more difficult decision. Next two numbers, so we're just playing around with these. One of the best ways to check, first of all, is to see how much there is in between each number, and then see if we see a pattern. So in between 3 and 4, there's 1. In between 4 and 6, there's 2. Between 6 and 3, and so on. And we can see that this pattern is just adding an additional 1 every time. So we get 31 and 39. Bag diagram here. So this is our outer bag here. The first element inside is 1. It is not inside an inner bag or anything. The next one is a set with 1 and 2. So that is inside an inner bag. Then we have an empty set. So that's just a bag inside here with nothing in it. The 0 itself is down here and the 2 is down here. Since we have 5 different items in the bag, notice this is one of the items and this is one of the items. And then the other 3 we would add in there to get a cardinal number of 5. Okay, an element that's in set A and B. So A is the set of all x such that x is an odd number. In other words, it's all the odd numbers, 1, 3, 5, -1, -3, -5. And then we know that y is a rational number between -4 and 4. So we could get we look for the odd numbers that are in between -4 and 4. We could use 3, -3, 1, 1 would be your four options there. Okay, this was a previous class. Obviously, we have way more than 4 girls in our class. But if we had a set of 4 girls, how many proper subsets are there? Keep in mind, 2 to the 4 is the number of all subsets. But one of those subsets would be the actual set of all 4 girls. And when we say proper subsets, we mean that we cannot include the entire set. We have to have some left over after we do our choosing. So we do take away one of those 16 to get 15. Notice there are other times when we take away the empty set. So do keep an eye out for what the problem's asking. Are you adjusting for the empty set? Are you adjusting for the set with everyone in it? Or are we just looking for all subsets, including the empty set and the entire set? Okay, here we have a Venn diagram. So we have two sets, A and B. Keep in mind that U is the universal set, so it's just basically what's inside this larger rectangle. The C is in both of these sets. It's in the intersection, so we put it right there. D does not appear in either A or B, but it is in the universal set, so it needs to come in outside. Here we have the intersection, which gives us C. Here we have a union, which means we're taking everything in A, all the elements in A, and all the elements in B prime. So the trick there is what's in B prime. B prime is anything not in B. So notice this is our B. The things not in B are the A, the E, and the D. So we're going to definitely include those. We're going to include everything from A, and when we put it all together, we get A, C, D, and E. B minus A prime. So we're starting off here with the B minus A. So we're starting off with B, these three elements, and then we're subtracting out any of those that are also in A. So we're taking away the C there. So that leaves us with B and F. Notice we didn't do anything with the A and E there because they didn't start off in B. We're only starting off with B, subtracting out what was in A. So that gives us B and F, and then we need the complement of that. So we need everything other than B and F. So that gives us A, C, D, and E, which just happens to be the same as the previous one. Okay, true or false. So here we have a set including 3, so like a bag with 3 in it. Is that an element of this set right here? Well, this set has 3 elements. One's a 1, another's a 2, and another's a 3. It does not have an element that has a set with 3 in it. In other words, a 3 tucked in its own bag is not one of the elements of this set. Now, if this had said the set with 3 is a subset or a proper subset of this set, that would have been a correct statement. So if we had had that sideways U or the sideways U with a line under it, that would have been a true statement. But this is asking us, is this thing one of the elements in the set? And that is false. Okay, so we have one of these problems we've looked at quite a bit in class. Knowing where to start off is key. For example, we don't start off with this first clue and just put a 22 on the outside here, because what we really need is we need all of the numbers at the end to add up to 22. So we've talked about one of the things, we're looking for a place with one region, but one way to do that is to find the intersection. So here we have A, B, and C. This is the intersection of all 3 sets is 2. So we could put that 2 there right away. And then after that, we could do any of these double ones. So B and C. B and C would be these 2 regions. So since we know that's 5 and we already know that's 2, that would give us this as 3. Here we have A intersect B, so we know that the total of these 2 regions is 3. We already have the 2 there, so we subtract to get 1. After that, we might do, let's see, what did we get? B and C, so we did these 2, maybe A take away C we could do next. So that would be these 4, but we're taking away the C here. So we're really only dealing with these 2. We know that this is 1 already, so that gives us a 3 up here. A take away B, similarly, would be these 4, but we're not counting these 2 regions, so it's just these 2. Since we already know that's 3, this would have to be 6. And then maybe we could move on down to this one. This one's a little trickier. A union B union C, so that's the entire thing, but it says complement. In other words, it's the opposite. It's all the ones that aren't in that huge region. Well, there's only one region that's outside of all these sets, and that's right here, the outer region. So that's 7. So notice that was only one region. We could have done that first, actually, if we wanted to, if we had noticed that. And then we know that the total is 22, so we add up everything we have so far, and I think that gives us a 0 here and a 0 here. Then we count the number in A. This is any element that's in any part of set A, so that would be the 3 plus 6 plus 2 plus 1 to give us 12. Same thing for the B and C. Okay, here we have 35 teenagers, 15 used Facebook, 20 used Twitter, and 4 used both. So 4 being in the intersection there, putting that first, and then we can get this 11 since we know the total Facebook users was 15. We get this 16 since we know the total Twitter users was 20. And after we do all of that, we can count these up: 20, 31 either used Facebook or Twitter, and we need 35 total, so that gives us 4 on the outside. So notice this 4 is coming from this 4 here, not from this 4. Okay, we have a few statements here. If Congress will not pass new energy legislation, so we're looking for Congress passes new energy legislation right here. And so that's represented by C, but we have if they do not, so we have a not C. And we have a conditional statement here with an if and a then, so that's where the arrow comes from. And so if they don't pass the legislation, then either we'll have global warming increase or we will develop alternative energy sources. So that's how we get the G or the A here. Okay, we have a truth table. Now we could distribute this negation sign. That would be not P and not Q, which would mean Q. So we could check right away to see that they're equivalent, but it does ask us to use a truth table here. So let's go ahead and use a truth table. So we have P and Q. We set up the 4 rows based on those options. Then we look here, what can we grab? Well, there is a not Q that we're going to need, so let's go ahead and flip all the values of the Q column. P or not Q, so we're looking at this column here and this column here. We have to have at least one true, so we get that in each case. Then we have not P or not Q, so we're just taking this column, flipping it all. Here, not P, so we're flipping the values of P, and then not P and Q, we're looking at this column, and since it's an and, we need them both to be true. Once we get these values, we're looking at this column and this column, because those are the two statements we're looking at. And since they are true in every case, they are logically equivalent. Again, that's something we could have seen with De Morgan's laws if we had used that. Okay, so we're saying whether this is true and then write the contrapositive. So if Jack won the Nobel Prize last year, he can dunk on a 10-foot hoop. That's true because this is false. If the first part of an if-then statement is false, then automatically the statement is true. It's vacuously true, automatically true. The contrapositive, we have to switch the order and negate both sides. So we're switching the dunk to the beginning and changing it to not. Same thing with the Nobel Prize. And this is also true because the truth value of an original conditional statement and a contrapositive is always the same. If this would have been false, this also would have been false. Okay, how many different ways to fill out answers on a 6-question true false? Set up a tree, you could look for a pattern, use simpler, however you want to solve it. Basically, in a 1 question, there would have been true, false, 2 options. Every time you add another question, you're basically multiplying by 2, so you're raising it by a power of 2. With 6 questions, you'd have 2 to the 6 options. And we did not talk about Pascal's triangles, so let's skip that one. Okay, our final truth table here. Notice there's nothing we can do in terms of a distribution here. We can't just multiply both sides by a negation or something to make this Q implies P. So we do need a truth table here. So we get our four rows. We know we need a not Q and a not P, so we can just flip the values of Q and then P. And if we do that, we can remember that as long as this is false, the whole thing is true, or if this is true and this is true, it's true. So there's only one case where it's not, It's the same as